Geosynthetics are defined as a planar product manufactured from polymeric material used with soil, rock, earth, or other geotechnical engineering related material as an integral part of a man-made project, structure, or system. Reinforced soil is defined as when a material with little or no tensile strength is combined with a material that has some tensile resistance to create a composite material of significantly improved characteristics and properties. Soil reinforcements have been around for thousands of years. As the Mesopotamians used soil reinforcements such as reeds mixed with soil in temples and pulverized calcium in roadways. If we fast forward approximately 3,500 years later, the first reinforced soil project in the US was taking place. This reinforcement project utilized backfill, steel reinforcing bars, and concrete panel elements to repair a large landslide in Southern California. By the early 1970s, this steel reinforcement technology was well established in several countries, and since then, nearly 4,000 structures have been built in more than 37 countries so far, using the concept of earth reinforcement. There are several forms of geosynthetics, including geotextiles, geomembranes, geogrids, geosynthetic clay liners, geocomposite sheets and strips, and geocells. The applications of these include separation, reinforcement, filtration, drainage, infiltration barriers, and protection. Geogrids are constructed of an array of holes and allow contact between soil particles on either side of the sheet. Geomembranes are impermeable layers that are often used to contain gases and fluids, and are also used for contamination control. Geosynthetic clay liners are factory-manufactured hydraulic barriers consisting of a layer of bentonite or other very low permeability material supported by geotextiles and mechanically held together by needling, stitching, or chemical adhesives. Geocells are thick, three-dimensional networks constructed of polymeric sheets which are joined together to form cells that are infilled with soil and sometimes concrete. Geocomposites combine the best features of different materials in such a way that specific applications are addressed in an optimal manner and at minimum cost. The geosynthetic reinforced soil integrated bridge system is one of the more recent applications of geosynthetics. It consists of three main components: the reinforced soil foundation, the bridge abutment, and the integrated approach. The reinforced soil foundation, like most geosynthetic reinforced soils, is made up of granular fill material and a geotextile fabric. The reinforced soil foundation increases the bearing width, which, from Terzagh's equation, results in an increase in ultimate bearing capacity for the GRS abutment. It also acts as an impermeable layer, preventing water from infiltrating into the GRS mass. The abutment is made up of compacted fill and geosynthetic reinforcement layers, typically spaced less than 12 inches apart. The integrated approach is made up of geotextile wrapped layers, which minimizes the differential settlement between bridge abutments and roadways, and forms a smooth transition between the two. The geosynthetic reinforced soil integrated bridge system completely alleviates the need for joints and cast in-place concrete. This system has proven to reduce construction costs and maintenance needs, while also accelerating the speed of construction. In 2011, the most powerful earthquake ever recorded in Japan struck off the coast, triggering tsunami waves that destroyed over 340 bridges for roads and railways along the coastline. Since then, geosynthetic reinforced soil integrated bridge system structures have been steadily taking the place of traditional bridge abutments. Geosynthetic reinforced soil structures have been constructed at more than 1,100 sites for a total wall length of more than 160 kilometers, mainly for railways including high-speed train lines. Among all the geosynthetic reinforced soil structures constructed, there have been no problems or failures during construction or long-term service during heavy rainfalls and seismic activity despite varying conditions. Another application for geosynthetic reinforced soils is in coastal defense structures. Urbanization of coastal areas has resulted in a large increase in infrastructure along coastlines. In order to mitigate the effects of increased population, coastal defense structures have been implemented along most coastal areas. The conventional strategies include mounds constructed of rocks which are set up as longitudinal defenses. These structures successfully reduce coastline erosion, however, they also cause environmental alterations which change the natural dynamic conditions. This dynamic has resulted in an increase in coastal flooding, erosion, tsunamis, and hurricanes. The earliest forms of geosynthetics in coastal defense were using sandbags to prevent the failure of coastal structures such as dikes or dams. Since then, they have improved greatly. Geosynthetic coastal structures maximize turbulent wave energy dissipation, but also allow passage of water and sediment.